So let's talk a little bit about the importance of temperature measurement. So again, our talk is going to slew between calibration, but also just measurement itself. Sometimes measurement is part of calibration with temperature. But whatever the organization is doing, what are the goals? Why is a particular measurement important to an organization? You know, what are the risks that are associated with it? Do you have if the measurement is performed incorrectly, what happens? Do you just have you waste product, or you cause a legal liability? Is there an area that you could end up in court because something isn't done right, or perhaps your supplier, your customer sends back your product and you have to rework it? There are a number of things that can happen, or just your reputation, your company's reputation is at stake. So there are many things. When you think about those risks, how do they impact you? Is it loss of revenue? Is it, again, loss of reputation? And then you have to balance what you're actually doing, right? So temperature measurement is an extraordinarily broad field in terms of the capability. You can measure something with a very inexpensive $5 thermometer. You can get a thermometer that somebody will give away to you probably on the show floor in the next couple of days, and it'll be some little thing that, you know, whether it's a label that tells you what your forehead temperature is or whatever, it could be free, to, you know, a few $100,000 to really measure temperature at a very low uncertainty. So obviously you can't afford anything for a particular measurement, but you can then strike the balance between what level of accuracy can I achieve at what cost. And we have some data on that. At least we can give you some broad terms. I don't try to advocate a lot of measurement in this. It's not a commercial presentation, although, you know, there will be a few slides of pictures of product on them. We could talk about them. Some will be ours and some won't be. And then also the concept of what needs to be done in terms of communication. What do you do with the data? I mean, if you're making a measurement that you care about, you're keeping it somehow, whether it's, you know, recorded into data that is stored on the product that you've just tested, or it's, you know, perhaps you're doing a calibration. Right? How are you storing that calibration data? Does your customer at the end need a calibration report? So how do you store and communicate that data? And then wherever you're doing a measurement, obviously you're overarching that is a calibration program, which really has all of the same characteristics. So I'm going to start with this little bit of information about accuracy and precision, and just review those concepts real quick. So accuracy is the device's degree of absolute correctness, or a measurement's degree of absolute correctness. And this is synonymous with uncertainty. Precision is the fineness to which an instrument can read repeatably and reliably. So let me illustrate the difference between those two. This is low precision and low accuracy. So you see you've got a center of a target you're trying to hit, and you've got a lot of different measurement points that are grouped very poorly. They're scattered all over. So that's low precision, low accuracy. That's not very useful to most people. This is why bother to measure kind of territory. But here's high precision and low accuracy. And this was an interesting case, because for many industries, what they care about is, can I get the same thing every time? And so being able to repeat the measurement is important. So a case where, give you an example, in the IR world, we had a customer that it was a steel mill, and they're rolling product out of a mill, and they wanted to make sure it was coming out at the right temperature. Of course, it's a moving product and it's glowing. So the way to do that is with infrared. But the problem is they needed it to be the same every time. And with the infrared, you could get, you know, it's a random number generator sometimes, depending on things. So they were using a contact thermometer to audit the process and then readjust the infrared system. So they didn't care about the absolute temperature, really. What they cared about is it was always the same temperature. So that would be an example of high precision but low accuracy. Low precision and high accuracy gives you something, you know, a group of readings that are centered about the target but scattered over a wide area. And that can be useful if you don't need very high accuracy. If your uncertainty isn't important, just it gives you something that's relatively close. And of course the goal is always high precision, high accuracy, tight grouping of measurements all at the center of your target. Unfortunately, that usually costs more money. So that's the that's the thing you have to trade off. So temperature measurement is one of the key elements to a successful process. To a heat treater, you're looking at a product, you have very tight tolerances if you're building something for the aerospace industry or even the automotive industry. You know, the part has to last 100,000 miles, or it has to endure a number of stress events without failing. So they have to keep those very tight. Obviously, if you don't do that, then maybe airplanes fall out of the sky, or suspension components break, things like that. A chemist is interested in maintaining a very consistent reaction. So if you don't do that correctly, maybe you don't get the right product, or you waste product mainly. A boiler operator is, of course, you know, his measurement is less critical. He just doesn't want his boiler to explode. Rubber molder, the reaction temperature of tires is pretty critical. So to get and the molds are very large, so you have to have the stuff at the right temperature. If you get it too hot, you over vulcanize things, you create problems with the tire. And if it's too low, you end up with not filling the mold completely, and you end up with voids in your tire. So these are issues. HVAC technician, they don't want customers to complain. Sanitizer. Oh yeah, by the way, you should turn your phones off. I don't mind the interruption. And if you have a question as we're going through, I don't mind interrupting, and we can go down a rabbit trail. That's fine. Or if we're going to cover it in the coming slides, I'll mention that as well. So feel free to redirect. You won't damage our carefully crafted pattern here. We'll get it done. We've got customers will sanitize an operating room with high temperature ammonia fog. So they'll basically close the doors and get outside and fog it down. Of course, you have to get everything up to a certain temperature, and you can't be in there. But it's critical, obviously, to kill a lot of pathogens. And for some reason, I guess going to a hospital is a bad thing, because it's usually where people get sick. So, blood bank, maintaining the correct storage temperature of blood so that it has its life. They have to actually record that on a continuous basis. Recording that, has to stay in a very tight window, or it's unusable. And the pharmaceutical plant too. These are another areas where if they don't make the product right, there's the legal liability. There's enough trouble with in any medical endurance or endeavor with being sued for something going wrong. So not only keeping track of a good measurement, but knowing what you did with it, being able to document it and retrieve it later on matters. So again, you're balancing your performance needs with your environmental requirements. What do you have to do? Sometimes you need to make a calibration in a particular area, and what you really need is a high accuracy bench instrument. But unfortunately, those are built for lab use. They don't transport well to the field. They also don't adapt to ambient temperature very well. Inexpensive handheld calibrators are useful out in the field, but then they have some problems with long-term stability, and they also then they have compromises when it comes to achieving the accuracy you might need. Or what they require is to achieve their accuracy, you actually need an ice bath to accompany that. We'll talk about an ice bath later. But those are obviously cumbersome to take out in the field. So in an ideal world, you'd have a portable, high accuracy calibrator that included cold junction compensation, could operate over a wide temperature range, and would be traceable to NIST, or some other National Metrology Institute. Now, once you have your data, you've got to communicate it and collect it somehow. And very often, still the method is, in this day and age, is pencil and paper. People write things down, use a clipboard, record all their calibration results or their measurement results, and put it in a file somewhere. Today, thermometers and calibrators can directly load this information right into a quality management system or whatever data collection system you're using. Things you got to look at are, is it a cabled system, is it wireless? There are a lot of standards out there. USB is a common one, so many devices work with USB. Bluetooth and Wi-Fi are also common standards in laptops. But there are other communication standards that are proprietary. And then once you've done that, you need some open software so that you can connect that all to your system. I know of I was talking about throwing out the pencil and the clipboard. I know of a not a local fast food chain, a national fast food chain that relies on its employees to actually measure the temperature of the product. They write that down on a clipboard, and then that gets stored somewhere for future use. So they're making sure that this data is collected. They're doing it. I mean, they're diligent about it. It's part of the responsibilities. At this time, you got to go check all this product and make sure that it's okay and it gets stored somewhere. And then that's their food safety program, and that's a good food safety program. But this is the room of the kid that they're relying on to do that job. I won't say that I actually know where this room is, but when it comes to data collection, there really are 4 levels. And they each have their own challenges and costs, but it's getting much better. So first is, of course, again, we said pencil, paper, and you file it. Well, that's actually easy to do, and that's actually not the least accurate way to do this process. Here is the least accurate way you can do this, and a very common is pencil, paper, and then you type it into a database. So not only do you have the problem of writing numbers down incorrectly, then you have the problem of transposing them. And studies into this accuracy show that it can be about 8% is the average of errors that people make transposing data from a paper to a database. And it can be as high as 20%. So this is actually the least accurate means of recording data. Now, thermometers can store data, and you can download it later, and that's certainly more accurate. There becomes the issue of sorting out, well, if I put 100 readings in a thermometer, I'm downloading at the end of the day, how do you get them aligned back up with the process and where you were measuring? This is an issue. And it's also not real time. What you've done now at the end of the day, you've got data. Well, if you're actually monitoring a process and your process is now out of control, you don't know it till the end of the day. So the most interesting methodology here is to use a real-time entry, wireless transmission back directly into a quality management system of some type, and now you can have real-time evaluation of the results and monitor your process and ensure that it stays in control. We have a customer that's using one of our data collection thermometers to monitor a blood bank. They have a bunch of refrigerators that they have to monitor that stay in compliance, and they have to do that in real time. If the refrigerator starts to drift off and they catch it in time, they can do something about it. They put their control limits tighter than their failure limits if they can, let's say, have some guard band in their temperature range, thinking, oh, we can fix this, I can address this before it becomes a problem. But if you don't know about it to the end of the day, you just throw away a refrigerator full of blood. Software is another issue, of course, when you start trying to automate data collection. Some systems are very proprietary. They've got this very small interface that they developed, and that's what you have to work through. Other systems are more open. They provide source code examples, work with the standard Windows Communication Foundation or whatever other open standards are out there. So that's something to consider when you're automating your data collection.